This is a gate problem on operational amplifier, and it appeared in the instrumentation engineering paper for 2023. And the problem is very nice. It encapsulates the properties of an ideal op-amp and also basic concepts of circuit theory. So let us look at this question. It is stated as the op-amps in the circuit are ideal. The input signals are Vs1 equal to 3 plus 0.10 sine 300 t volts and Vs2 equal to negative 2 plus 0.11 sine 300 t volts. The average value of the voltage V0 is dash volt, and they want the answer to be represented by rounding off to 2 decimal places. So this is a 2 marks question of numerical type. This is the corresponding circuit, and if we look at this circuit, at least if we look at this portion of the circuit, then this is the initial stage of the instrumentation amplifier. And the only modification that they have done is, instead of connecting this resistance and the other resistance to two input terminals of another amplifier, which forms the difference amplifier stage in an instrumentation amplifier, instead of that they have mentioned that we need to find out the voltage at this node. Now, before going forward with the solution, let's just revisit our understanding of superposition theorem. So with superposition theorem, if you are given a linear system, and it could be a linear circuit also. So if you are given a linear system, and let's say there are two voltage sources which are applied to this particular system, so V1 and V2, and we are interested in measuring what is the output voltage, let's call it V3. Then with superposition, this is a divide and rule policy. So you just allow only one source to be present in the circuit and deactivate all the others. So with the first one, we are applying V1 and we are deactivating V2. So with a voltage source, deactivating means you are making it 0 volt. And then find out the voltage across the output terminal and call it, let's say, as V3 dash. Similarly, repeat it for all the other instances. So the only other instance here is that we apply V2 to the circuit and we disconnect V1, or we make V1 equal to 0 volt. We are deactivating V1, and then we go on and measure the value for V3, and we call this as V3 double dash. And therefore, if we had this original circuit, then V3 would simply be equal to summation of these individual outputs. So V3 is equal to V3 dashed plus V3 double dashed. Now that being said, if we refer back to the circuit that is given here and we just modify it so that it's in a form that we have already seen, because this is the initial stage of an instrumentation amplifier. So I have simply drawn it in that fashion, and then we know that the op amps are ideal. Therefore, the concept of virtual short is applicable, which means that voltage at the non-inverting input terminal should be equal to the voltage at the inverting input terminal, as there is presence of negative feedback. So if this voltage is at Vs1, voltage at this node will also be Vs1. Similarly, for this second op amp U2 also same stuff. So you have Vs2 here, and the voltage at this node will be Vs2. And let's just say that the voltage at the output node for the op amp U1 is called as VO1, and the voltage at the output for the second op amp U2, we name it as VO2. Now, if you concentrate only on this part of the network, then a current, if it flows from VO1, should end up flowing up to VO2. and then after this the current can take this route through R, as also it can enter the input terminal of the op amp, or maybe it can exit, some current can exit from the output terminal of the op amp. So framing this equation, VO1 minus of V0 divided by R, which is this current, must be equal to V0 minus of VO2 divided by R. And so from here, we can note down the value of V0 as simply the average of these two voltages. So this is half of V01 plus V02. In fact, with little practice, you don't even need to solve this. If you find a circuit like so, you can simply note down V0 as the average of the voltages which are present at the two extreme points. So our objective is to find out the average value of V0, and we have already found out that this is simply equal to average of these two values. Now let's concentrate only on this part of the circuit. If you concentrate on this circuit for U1, then what we have here is a voltage source Vs1. What we also have here is a source Vs2, and then there are two resistances, R and R. And we can apply superposition here because there are two sources. So we can write for the first one, we are suppressing Vs2, we are making Vs2 0 volt, and we are only allowing Vs1 to be present in the circuit. And this topology is that of a non-inverting amplifier. And we know that with a non-inverting amplifier, the expression for the output voltage will be 1 plus feedback resistance by the resistance which goes to ground from the negative input terminal multiplied by the source. So this is 1 plus R times Vs1 equal to 2 times Vs1. In the next instance, we repeat the superposition theorem when we are deactivating Vs1. So see that Vs1 is connected to ground here, and we are allowing Vs2 to be present in the circuit. So now it turns out to be an inverting amplifier. And with an inverting amplifier, we know that the output voltage is simply negative of this feedback resistance by the input resistance multiplied by the input source. So this is negative of R by R multiplied by Vs2. So this is negative of Vs2. And then combining these two outputs, that means V01S dashed and V01 double dashed, will lead to V01. So summation of these two is given by twice Vs1 minus of Vs2. Now we don't need to repeat this for the other part. With this connection for U2, you can find that this is a symmetrical circuit. So with a symmetricity, the easiest way to solve for this V02 is to look at this expression and then simply flip the values for the voltages. So VO2 becomes equal to 2 times Vs2 minus of Vs1, and therefore we have the values for both V01 and V02. So this V01 and V02 we have derived here using superposition theorem. So going back to the original question, our objective was to find out the DC value for the output voltage, and we know that V0 is equal to half of V01 plus V02, and therefore if we substitute the values for V01 and V02 derived in the previous slide, you can find that it comes out to be half of 3 plus 0.1 sine of 300t minus 2 plus 0.11 sine of 300t. These values are mentioned in the problem, and therefore this simply becomes equal to half of 1 plus some sinusoidal component arising out of these two expressions. And we can generalize this as A sine of omega t. Now note that our objective is to find out the average value or the DC value of the output voltage. And we know that the average value of a sinusoidal signal is always zero. Therefore, we are not bothered about this sinusoidal component. We are only bothered about the DC value. And therefore, the average value for V naught is equal to half volt or 0.5 volt. So the answer to this problem is 0.5 volt.